Good evening. Good evening. This is the extra session for fundamentals of additive manufacturing. We good evening. This is the extra session for fundamentals of additive manufacturing technology. So here we'll discuss on the concepts and the courses which we covered in the first 5 weeks, uh, just a revision of all those concepts. So we'll start with stereolithography process. We'll start with the questions and some concepts related to the introduction portion. Okay. So the first question is starting material of the stereolithography method is in the form of solid, powder, liquid, wire, or gas. Now stereolithography is in fundamental of it in additive manufacturing. There are total 7 methods, out of which stereolithography is the first method. It is also known as VAT polymerization, as you can see written over here. So VAT consists of two words. One is VAT and is polymerization. So what is VAT? VAT is a container. This is a one second. VAT is a container. Now, okay, this container is known as VAT. Now, in this additive manufacturing process, the solidification takes place because of polymerization. So that is why we have VAT polymerization. So we have different bonds in the resin, and now in this polymerization process, the solidification takes place through polymerization, solidification. We have resin and we have different bonds within the resin. Now the bond, when UV rays fall on this resin, this solidifies. So combination of these two words is VAT polymerization, and this process is also known as stereolithography. So combination of these two is known as VAT polymerization. Now the resins are bonded resins bonding occurs UV rays solidification. Now in the stereolithography, I have base material or starting material it is in the form of liquid, as we can see. Okay, so the resin which we put in the vat, it is available in the form of liquid. Now the solid, wire, gas, powder, we have to find out. This we will also discuss. Okay, no, so we will discuss in detail where each of the starting material will in the solid. Okay, so let's segregate. In FDM it is wire. Okay, so solid, we have sheet lamination, binder jetting, powder jet fusion. The liquid is in stereolithography. In binder jet, we use binder as liquid. Okay, in material jetting also, starting material is in the form of liquid. Wire is in FDM and DED. Okay, now FDM has also some other name like fused filament fabrication. Okay, fused filament fabrication. We usually use in journals fused filament fabrication. We do not use FDM. It has a trademark or copyright to it. Now we will discuss so next is what about gas? Now is there any process where we can use gas? So there is no process. But we use inert gas in powder bed fusion. Okay, that we just recently discussed in our class. Inert gas. Yeah. Okay, so now we will go to the next question. So the process which extrudes molten plastic through a nozzle, which is the process. So molten plastic comes out of the nozzle. The process is known as fused deposition modeling. Now we have so we know when it is plastic selective laser molding, we have a powder. In DED we have powder or wire. We have wire and plastic. 1.75 mm or 2.85 mm. No nozzle. There is a vat container, liquid inside the container. Liquid, vat. Okay. So, okay. So, this was about the different process. Now, next question will go. Here in this question, we have some images and it is being asked in which support is required to realize the features of the object. Now, we have to see where inaccuracies, more inaccuracies rest, how support structures need to be, we need to decide how many, how, where and what support structure to give, because there are support structures like linear, tree like. So this is a sort of FDM process. Okay. Now, support is required to realize the dash features of the object. Identification of the region required support is carried out at the dash stage. So, the correct option is overhanging and pre-processing. Before we give the files for printing, STL files for printing, we have to give the supports so that it will be printed properly. And these are the overhanging support structures which are being given. So, suppose we are printing like this. When we reach this layer, there is no material below this layer. So, this material will start to fall down. So, to avoid this, we provide enough support so that it will be. Now, this support can be removed manually, or we can use. Suppose we are printing ABS, then we can use other support material like HIPS, which can be removed by dissolving in limonene solution. Now, we have different length horizontal overhangs as it is written here. Okay, so if I am increasing the length of the overhang, there is lot of inaccuracies. These are inaccuracies. Okay, now to avoid this so that it will be printed steadily, we will give support here. This is support. Okay, we will give supports all over here. So, this angle of overhanging, at which range we have to provide, that there is also a range to provide the support structure. Now, in FDM, this range is 30 to 90. Okay, for the, suppose there is a support, the support is 30 degree. Okay, up to 30 degree, till the printer will print this. Okay, but so till 30 degree it will print easily. There is no need to provide support structures. But After that, some you will need some support structures. Now, in some complicated structures, we should not use support structures so that we won't destroy the uh, our specimen. Okay, and we cannot remove the support structures easily in that process. So up to 30 degree we can print without, but when it is more than 30 degree we have to use external support structures. Now in most of the printers supports are of street like, linear and tree like support. Okay, linear, tree like. Okay, linear are like this, zigzag. Now the tree like are, for linear support we have to put more support. So for tree like we can put less. Okay, this is the tree like support. Suppose this is the overhanging and we are using some tree like structure. So we can use it with we can save lot of support without when we give linear it will be more support we have to provide, but if we like support we can use less support, but tree like supports are difficult to remove, but linear supports are easy to remove. Okay, now in powder bed fusion process we have a bed and a component is sitting on that bed only, and and between these overhanging features we have a powder particles. So now in powder bed, if the angle is above 45 degree then we need support, but in FDM we need it at 30 degree itself. Powder bed it is at 45 degree. Powder bed more than 45 degree we need support. Okay, now we will move on to the next question. Now, as per the occurrence in additive manufacturing process, the following we have to put the following operations in correct order: generation of support structure, generation of CAD model, generation of the steel file manipulation, removal of support. So the correct option is generation of, first we have to prepare the CAD model, then we have to do the for pre-processing, which includes like if we have to give 3D, we have to give support structures, we have to do the slicing. That is, this happens in this slicing software, generation of support structures. Then is STL file manipulation, and next is removal of supports. Okay, so now here we have a primitive lattice structure. So this is the CAD model of the lattice structure. After that, we generate STL file has been generated. Then in any slicing software, the slicing is done and with G code is written. This is done by the software itself, because now when you print the file, the printer will understand the format in GX code. Okay. So the software will convert the file from .stl file to .gx code. Okay. Now GX code is nothing how the printer, the conversion of the triangles or facets in an STL file to a G code manner, that how the printer will move from each point to generate the structure. Okay. So in the additive manufacturing process, this printing will be done. So this is an example of a primitive lattice structure of a triply periodic minimal surface. Now this CAD model is designed in usually MATLAB. Now, now how these codes are written and how these STL files are formatted in slicing software. This is our these we do in week 2 we will discuss. Now one more thing, here in slicing software we also give the printing temperature, material, how much density we are printing, what all these things also we put in the slicing software. Okay, now this is the final product. Now this is the FDM machine. So we can do stereolithography, VAT polymerization, so many things we can use. So this is the generic process of CAD to part conversion. So if a metal printing we are doing, powder bed fusion, DD process or sheet lamination. But in sheet lamination it will be highly complicated to do that. Okay, next. So this is the correct option. Next question. Next question is how many triangles are required to complete the STL file of below geometry? Now, so this is how many minimum triangles are required to complete the STL file of the below geometry. Now, here in this we have six spaces. So are required to complete the model. So thing is here how many minimum triangles are required to convert this model into STL file. Okay. Now this cube has six faces and each face can be divided as two triangles. So total it becomes 12 triangles. You can do more than two triangles, but this is the minimum number. So this is the minimum. So 12 is the correct answer. So below we can see this picture how the pixels triangles are. Now digital image is composed of pixels and STL file is composed of triangles. So more the number of pixels, better is the resolution. Similarly here, more the number of triangles, better is here. So suppose you have a 10 megapixel camera, you have 10 million pixel per snap. Now in STL file also, we don't have pixel, we have triangles here. Why we use triangles? When we convert your CAD model to STL file, the size of the file is okay. So STL file is the format. So what we do in STL is we convert the whole geometry into set of triangles. Small, small, small. These are the small, small triangles. Okay. Now this triangle is made of edges and vertices. So, so, so more the number of triangles, better will be the quality of your final product in terms of dimensions. So suppose you take this nose and we take only two triangles. It will, so our nose, if you do it with only two triangles, our nose will be pointed. Okay. So more the number of triangles, better will be a quality, and better will be accuracy, not quality, better will be accuracy, as our dimensions will be more accurate. Next question. Which of the prototyping are associated with additive manufacturing? Virtual prototyping, physical prototyping, virtual and physical both, or none of the above? So we have a journal also, virtual and physical prototyping. Okay. What is virtual prototyping? It is a software based software. We use a software which where modeling a system, simulate and visualizing its behavior under real world is done. But but we are not creating the part physically. Okay. Now, physical prototyping is when you are really creating a part and testing it in experimental conditions and in real life. But here we are doing it in modeling. In some software like Abacus or Ansys, we are creating the virtual image, virtual prototype. We are creating the virtual. Now, in additive manufacturing, we are doing physical prototype. That is, we are creating the part in real life. Okay. Now, suppose we are printing a sample. We are printing this specimen. Okay. So, here we can print it. So, first what we do is we create a virtual model and simulate it, check the deviation, deflection. So virtual prototyping is before the final printing. You can you can always check whether the how the your final product will work under some particular condition. So that can be done in Abacus, Ansys, or various other softwares are there where you can do the modeling and put those put your loading conditions and try to visualize how the object will behave. Because once you print and it is not accurate or it is not as per your required criteria, then you will always lose money. Because if we print such parts, small parts in metal also, it will go around 80,000, 90,000. So to avoid this much loss, we should always go for a virtual prototyping. So the correct option is, this is not correct. The correct option is virtual and physical prototyping. Okay. Fine. Now There is also a term rapid prototyping, which was in the market before 3D printing came, where we produce the final parts before and it was in a rapid manner. Okay, so this both can be done. Okay, but when we are considering with additive manufacturing, only physical prototyping is done. Okay, fine. So what kind of production system is suitable for additive manufacturing? Mass production, mass customization, fabricating, conforming, cooling channels, fabricating lattice structure. Now, now for a for mass production, additive manufacturing is not suitable. Suppose I want to print a small bottle. I cannot so these type of things or requirements should be met with mass production, as it will be cheaper. So print a single bottle, it will take consume more time, and also everything is there, electricity consumption time for a single, but for mass production this is a faster and it will meet larger demands. But for so when we have to choose the additive manufacturing process, so this is mass customization. So here there are some graphs. Okay, we'll compare our products with the graphs. Additive manufacturing, traditional manufacturing, here you can see, and here we have a high complexity fabricated at low volume with low reduced cost, and serial production at high volume systems. So we have traditional manufacturing process, which may be milling, machining. Other is additive manufacturing. When the production volume is less, so here we can see when the production volume is less, the cost is very high. Okay, and here when the production volume is less, cost is very high. Okay, when the there is when the cost is very high, there is no need to use other processes. So we have to design a product in such a way that the final product should we are getting, so it should be better than the uh, products which are manufacturing with the traditional manufacturing. So here we have a serial production of high volume system. Now here you can see a high complexity fabricated at low volume with reduced cost. Next, here we have a serial production of high volume system. Now, and here we have a light weighting by high complexity. Here we should use additive manufacturing. Here also we have a light weighting by high complexity. Here we should use additive manufacturing. Now, this is also high complexity fabricated at low volume with reduced cost. So when the final product is very simple, no need of using additive manufacturing. We can do it with our traditional manufacturing. But for this complex system, we should use additive manufacturing. Now we have a unit cost on the y-axis here and the production complexity on the x-axis. Now when the production complexity increases, we have to use additive manufacturing. When the production complexity is less, we can use for traditional manufacturing. Similarly, in production volume, when our cost is less and production volume is less, we can use additive manufacturing. But when our production volume is more but cost is more, then we should go for traditional manufacturing. So we have to see how the feasibility what is economical. So these all things we have to notice. Feasible, economical. Okay. Now this is a so suppose we can take the example of a conformer cooling channel as it is written. So this is traditional manufacturing. Earlier it was not possible. Suppose this one we are considering here. Now here we have the cooling channel. So before it was not possible to manufacture this type of conformal cooling channel. Okay, but now it is possible to manufacture those. In the traditional manufacturing process, it is not possible to manufacture such cooling channels. Now we can print them using additive manufacturing process. Okay. Ultimately, so it is economical when the complexity is very high. Now, what is this? There is an engine where from the sides we have to make a channel. That means that is a conforming cooling channel. So that will transfer the heat and it will behave as a heat transfer agent. Mass customization we already discussed and fabricating lattice structures also we discussed. Next question. Okay, mass customization means when we want a customized product, some person wants exclusive design, some other person wants some other exclusive design. So in that case, when you have to change the design again and again, in that case also we can use additive manufacturing. Okay. Next question. So which of the following has non-uniform porosity? Foam, bones, single crystal diamond, functional graded diamond. So I have marked the options. Foam, bones and functional graded matters has non-uniform porosity. Now these are, you can see these are porosity. Now here, see these are the voids or porosity. Now here you can see this is a sheet based diamond triply periodic minimal surface. Okay, now then from bottom to top as we are going, we can see the voids, the whole voids, holes or voids, these are increasing. Okay, so that means there is a gradation. That means this is the term where it is known as functionally graded. Functionally graded. Okay. Now your diamond is single crystalline, but your bones and foam is also functionally graded. That is, the porosity varies from one point to another. Suppose this is 50%, this may be 20% porous. This is porous, not the density I am writing here. Okay, 20% porosity. So now relative density is equal to 100 minus porosity. So density is decreasing porosity is increasing. Okay, that means if you have a 20% porosity here, that means the density is 80%. If you have 50% porosity here, density is 50%. Now, the foam is also non-uniform. We cannot control the pore size. Somewhere it may be 50 micron, other it may be 20 micron or 80 microns. Now bones we know as per our requirement of body, it has different porosity. Now this is an example which has of a porosity structure which is generated in MATLAB. Next question. Now this is a straightforward question, like which of the following STM standards is additive manufacturing? The correct options are ASTM F42 and F529. Now ASTM F42 is the standard additive manufacturing in all these 7 additive manufacturing processes. Okay. Now, so these standards have given a definition of additive manufacturing. Okay. These are some different standards. Okay. This is not related to additive manufacturing. It is for tensile testing of plastic and 2-1. This is also not correct. It is used to calculate the porosity. Okay, the ASTM standard. It is not associated with additive manufacturing process. Okay. Now, I have here just put the different additive manufacturing process: VAT coating polymerization, material jetting, material extrusion, binder jetting, powder bed fusion, sheet lamination, directed energy deposition. Okay. Now, we can see that the first 3 processes, they are the metal parts indirectly and the metal parts directly. Okay, that means now we'll understand what it is. So, in VAT polymerization, as we have said, we have a VAT and resin. VAT means container. So that will, and this laser will scan. Laser is in the form of UV rays. It will scan and cure our resin. So instead of laser, I can use a printer also. The printer which are using in DLP, that will print whole layer in one go. So that will be faster as compared to the laser. The process is same, but it is also known as VAT photopolymerization. There is material jetting. Material jetting will be used for wax, sand. It is also here, like in process of material jetting, the drop multiple materials are jet at a time. So in FDM process also we can use dual material. but accuracy is very less. But in material jetting, your accuracy will be low, very high. Sorry, the material is coming in the form of jet. Droplets will be deposited, and the accuracy of the particles will be printed product will be much higher than FDM process. The material extrusion is selectively extruded through a nozzle or orifice in layers. So here plastic, nylon, as you can see, even nowadays sand also we can use. Now we are binder jetting, where we have powder particles, and from a nozzle we jet a binder, and that we have a laser. Now in binder jetting we have to remove this binder after that removal is required, but here sintering is required. Without sintering, but in powder bed fusion, like we recently discussed this also, so we can use the final product immediately, no sintering is required. Next. Now the materials, so you can see polymers, fibers, then it's sheet lamination process. So it is a hybrid process where it is using machining as well as 3D printing also. Here layers will be printed in the form of sheet, and two sheets will be joined with the help of some binders. Okay, ultrasonic welding or frictional welding, etc. Next is directed energy deposition. This is used for large scale application. Here we use a material in the form of wire, and energy source is in laser or arc. In like the arc we use in weld. Arc in the form of electron beam. In powder bed fusion also we have a laser and electron beam. Okay, like you see here, laser and electron beam. But here the materials don't have very high reflectivity. When we use a laser with this type of material, we use a deflector for no deflection. So in this cases also, to avoid deflection, we use electron beam, because electron beam does not deflect, but it will be costlier. Electron beam powder bed fusion is costlier and accuracy is also higher. In directed energy deposition, we have a nozzle in the form of wire or electron beam, and from that nozzle only laser will melt the particles and deposit it in the form of beads. This was a summary from, this is the potential of direct energy deposition at the manufacturing process. So here large scale additive manufacturing process can be followed. Okay, you can see the scale of the this is built in 90 days, diameter is 58 inches and the height is 72 inches. It took 90 days for this to be printed. This is a wall nozzle fabrication. Okay, this can be done in traditional manufacturing process. Why we did in 3D manufacturing, 3D printing is that if you see, you can see the internal structure of this nozzle. You can see a cooling channel. This is the internal structure. This is the cooling channel. These cooling channels had to be printed using additive manufacturing process. These cooling channels. This type of component manufacturing with traditional manufacturing process, it is difficult, and it will not be that much accurate as per additive manufacturing process. So this is a perfect example where we can decide where we can use additive manufacturing process and where we can use additive manufacturing process. Okay, so this was all about the initial introduction of additive manufacturing process. Next we will move on to the next portion. So grid cutting method, there are two area filling methods. Two main steps to convert (3D) model into control data of additive manufacturing machine. One is slicing and another is tool path planning. Now there are three different types of tool path. So we will gradually understand what is grid cutting method. Now there are three different types of tool path. That is, one is corresponding to the scanning of outer contour. One is scanning of inner contour, and one is scanning of inside area, which is known as area filling. This is known as area filling. Now diagrammatically if we represent it, it is, suppose this, if we consider it as outer boundary. Okay, now in this outer boundary, suppose now we have this again one inner boundary. And in this area we want to add material. So, and here we don't have any material, no material. How to add material to this part? So here in this concept we require area filling method. Now so this method of adding the material in the required zone is called as area filling method. Zone is called as area filling method. Now let's take an example of laminated object manufacturing. Here, where in this case the raw materials are in form of sheets. Now in LOM process, raw material are in form of sheets. So now we have to remove this portion. How to remove this portion after completion. This is the part, okay, outer boundary, inner boundary. Now this region is with material. This region is with material will also be separated out. Separated out. So how to remove the portion after completion of the part? Now in this case we have, now for this thing operation grid cutting is required, is performed. That means this is a combination of x and y passes. Now this here in this case the cutting operation, like after completion of the grids, user can easily remove the grids. This will be in this grid format. User can remove these grids so that we get the outer periphery corresponding to the desired object. If we do not provide grid cutting, it will be difficult to obtain the specific part out from the object we produce. Now moving to the question which we had. Now, grid cutting method includes negative of the material region in a slice. Material cutting or addition is governed by resolution of pixels. For removing the unwanted part, none above. None above. So, uh, so this method involves dividing an image into a grid of small squares or pixels and then performing various operations on these pixels to achieve desired changes in the image. So negative of the material region in a slice, this means this does not accurately describe the grid cutting method. The negative, it is not commonly used in the context of image manipulation through grid cutting. Now material cutting or addition is governed by resolution of pixels. This is the correct explanation, one of the correct explanation. Here the grid cutting image content with each grid cell or pixel can be manipulated, added or removed based on the resolution of the image, meaning that changes are made on a pixel by pixel basis. Now for removing the unwanted part, yes, grid cutting method also removes the unwanted parts of an image, but this is not completely. These both are the correct options. It involves more than just removing unwanted part. It also involves pixel level manipulation. So these are the correct options. So in this case we have uh, the completion of grids. User can easily remove the grids later on. Now if we also okay, so next question. Okay, now here this question is little it's not like we'll discuss what is exactly area filling path. So the area filling path these are, one of them is grid cutting. What are the methods involved in area filling? So we will discuss all these. So area filling paths are grid cutting, pixel, path and mask. Now grid cutting, which we just Saw, it is for removing the unwanted part. Pixels is material cutting or addition is governed by resolution of pixels. Now path includes the different types of path to be followed, like raster, zigzag, contour, spiral, hybrid, continuous, and space filling. I'll write it here. Space filling also. Hybrid, continuous. So these are all belong to path. Now we will discuss like what are in the in our CAD. So these are all the. Is my screen visible? Just wanted to confirm.
Yes, ma'am.
Okay. So these are the various area filling parts. Now we'll discuss what are the about the different area filling tool paths in the following question. So now area filling tool paths in the context of computer design or CAD or CAM, area filling tool paths are used to fill regions of a shape with materials or patterns. The different parts have different distinct advantages depending on specific requirement of the manufacturing process and the desired outcome. Now, raster, zigzag, contour, and zigzag and contour path. Now, out of these four area filling tool paths, which of the following method is most advantageous? So first we'll understand about all these methods. Now, raster is now raster is simple, efficient, and robust with any boundary. Now we have different types of raster. X raster, raster, y raster, and xy raster. Now x raster. Suppose this is your tool path. Now this is your object. The tool will, in x raster, it will move from in the x direction, from this side to this side. So this, let us consider this as, and here stresses will be in along sigma 1 and sigma 2. Now suppose, let's consider object moves from 1 to 2, and then again from here it will move, this is the dotted line, 3 2 to 3, then this, in this way it will come to 4. Now this 3 2 to 3 will be in air. Okay, it will be the retraction. Now for y raster, the tool will travel from 1 to, then it will come from in air, this is 3, it will reach 3, then it will again travel to 4. Similarly this will be done. Now xy raster means this will be along both x and y direction. This is xy. Now dotted lines are movement of the tool in air. So xy raster, this is done to get the homogeneity in the deposited material property. Xy raster, this is done to get the homogeneity in the deposited material property. Now this is about the raster path. Next is the zigzag tool path. Now in the zigzag tool path, or this is also known as direction parallel tool path, this is the most commonly used tool path in additive manufacturing because it is less build time and fewer transition motions. Now here what happens is, let's say this is our object which is model. Now the tool is here, it goes here, then it travels along this, the darkened portion, I am just circling it, then it again comes to this position, it travels along this, then it moves, then it again travels along this, and it comes back here. So what happens is, in the ends, these are the ends, tool does not lift, it moves along this path. It keeps on adding material and reaches to the, it keeps on adding material and reaches to the next line. So boundaries of the contour are approximated by linear edge. However, due to the discretization errors, like here some discretization errors may occur which is not parallel to the tool motion, and that is why the outline is sometimes poor. So this leads to poor surface quality of the printed part. But this has less build time and fewer transition motions. Less build time, fewer transition motions. Now in these ends, tool does not lift. It keeps on adding material and reaches to the next line. Now because of this, now this is very important. Now boundaries of the contour in this zigzag path are approximated by linear edge. However, due to the discretization errors, on any edge which is parallel to the tool motion discretion, the outline is poor and leads to poor surface quality of the printed part. Now we understood what is the raster path, zigzag path. Now next we'll move on to contour path. In contour path, also known as contour parallel model offset, here this is applied by offsetting the contour of the geometry, like a series of offsets starting at the outer boundary, and this progresses towards the center. Now creates a series of offsets starting at the outer boundary and progressing towards the center. Now next is what is zigzag plus contour path. Now this is a combination of different approaches for benefits. Like here we fill few lines from outer by contour path parallel, and from inside we use zigzag. Now contour parallel from inside, why we don't use here? Next is zigzag plus contour path. This is the most advantageous part combination of different approaches for benefits, printing benefits. Okay, so here we fill few lines from outer by contour path, parallel, and from inside we use zigzag. So why we don't use the contour parallel inside? Because this will leave cavities. Cavities means this will leave some voids or surface which will create surface defects. Contour parallel from inside will leave cavities or voids. So, but this is zigzag, and combination of zigzag and contour path is the most advantageous out of all the methods. Okay, next we'll solve a numerical. So here in this question we have been given the ASCII format of STL file, which is the vertex of the three triangles. Now it is written that if a triangle is translated plus 3 unit along x-axis, then plus 3 unit along y-axis, and then plus 3 unit along z-axis, what will be the unit vector corresponding to the new facet normal? So many people had doubts regarding this question last class. So that is why I have taken again this question and we'll solve it. Now we will take these vertices and start solving the question. Now, according to the question, we have the triangle whose vertices are P1, P2, P3. We will name it as, this is 1, 1, 1, 0. This is 1, 2, 1. This is -2, 2, -1. Okay, I'll just show you the question again. 1, 1, 0, 1, 2, 1, -2, 2, -1. Now, it is asked that we are rotating along x-axis 3 unit, along y-axis 3 unit, and along z-axis 3 unit. Now, what will be the unit vector corresponding to the new facet norm? Now, we have a rule that in translation, normal will not change with when it is rotated with respect to any axis. Maybe let it be z-axis or y-axis or z-axis. So, we need to completely ignore this part. We need not consider from here to here. We do not need to worry about this. Okay, so we will solve the question. Now let's consider this as v vector, this consider this as w vector. Okay, now v is equal to p2 minus p1, and this will be 0 I cap plus j cap plus k cap. W will be P3 minus P1. This will be minus 3 I cap plus j cap minus k cap. Now we need to calculate the two vectors and take the cross product. Okay, calculate the two vectors and take the cross product. Now How we will find the first product? This is I cap, J cap, K cap, 0, 1, 1, 0, 1, 1, 3, minus 3, 1, minus 1. So 0, 1, 1, this is 0, minus 3, 1, minus 1. Now we will multiply. This will become I cap 1, minus 1, minus 1, minus 1 to minus 1. Now minus J, I cap minus 1, minus 1, minus J, plus 3, plus K, 0, plus 3. This will become minus 2 I cap, minus 3 J cap, plus 3 K cap. Now we will take out the coefficient of normal vector. Coefficient of unit normal vector. This will be minus 2 I cap, minus 3 J cap, plus 3 K cap by root over of 2 square plus minus 3 square plus 3 square. Now this will become minus 2 by 2, 22, 4, 9, 13, plus 9, 20. Minus 2 by root 22 I minus 3j by root 22, and this will be plus 3k by root 22. Okay, now upon solving this we will get minus 4.42. This will be 0.63 and this will be plus 0.63. Now according to the option, minus 0.42, 0.6 minus 63, option 2 is the correct answer. So in this way, if it is given the unit rotation of by some units, you need to take into account this part, that if in translation normal will not change in x or y or z axis, and here it is asking what is the unit vector corresponding to the new facet normal. Okay, so the next question. Now here, in a sphere has to be built by an additive manufacturing process in which the triangles of the STL file with facet normal are at an angle more than 45 degree from the build direction, require a support structure. Now select the correct option. More than 2 by 3 surface area of the object will require support, less than 1 by 4 surface area of the object will require support, less than 1 by 8 or more than 5 by 6. Now we will understand the question and solve it. First we will draw a sphere. Okay, now here it is, consider this is the build direction. So let us consider the sphere, and the build direction is this. Now we know as per the rule that when more than 45 degree is we have the angle, support is required. Support is required. So now we will divide the sphere into, first we will divide it into 4 parts, and I'll explain where all supports are required. Now divide the circle, step 1, divide the circle into 4 parts. Now this is considered 90 degree, this is 45 degree. (45 degree, 90 degree and 0 degree. Now here along this part the build direction is at 0 degree with normal. Build direction is, this is the build direction, this is the normal. Okay, now here it is at 90 degree. We need support. Same again here, we don't need support. Here we need support. Now at this 0 degree we don't need support. When it is more than 45 degree, like here in the condition, we need support. So in here when it is 90 degree we need support. Now we'll again divide the sphere into more parts. Consider this the sphere. Earlier we divided into 4 parts, now we'll again divide into 8 parts. Okay, now here this is 90 degree, 0 degree, 45 degree, 45 degree, 0 degree, 45 degree, 90 degree, 45 degree. Now after dividing into more parts, we see that this from here, if we consider 0 degree, this is 45 degree, this is more than 45 degree. So this part will need support. Now here it is theta is greater than 45 degree, this part will also need support. Here theta is less than 45 degree, here theta is less than 45 degree, here theta is greater than 45 degree, we will need support. Here theta is greater than 45 degree, we will need support. Okay, so according to this, if we see now answer now according to the question, what is the question? Like less than 1/4 surface area of the object will require support. Now here it appears that half of the object requires support, but that is not correct. Now in our lecture, as explained by sir, we know that in the manipulation of STL file, when the facet normal is upward, that does not require support. Slide 7, it is mentioned by a professor in manipulation of STL file that when facet normal is upward, we do not require support. Now in all these in this condition, the facet normal is upward, so we do not require support. So answer is not half, it is 1/4 answer. 1/4 of the object requires support. Not half. So the correct option is less than 1/4 surface area of the object will require support. I hope this is clear. Let's move on to the next question. So here in the question we have been given three triangles which require the support structure in STL file. Assume the bell direction is plus z and the base is at z is equal to 0. Find out the volume of the support. Now we'll first understand where this is triangle number 1. Now this is triangle number 2 and this is triangle number 3. Okay, now here we need consider this that we need support. Okay, now we need to find out the volume of the support required. So let's calculate. Now I'll just write the vertices of each triangle first. Triangle 1, the vertices are 20, 0, 12, 18, 12, 15 and 15, 3, 15. Okay. Triangle 2, it is 18, 12, 15, 15, 3, 15 and 8, 10, 12. Triangle 3, I'll move on to the next page. Triangle 3, it will be 15, 3, 15, 3, 15, 10, 0, 10 and 8, 10, 12. 15, 3, 1, 5, 8, 10, 12, 10, 0, 10. Now the method is that we need to calculate the area of each triangle, and so after calculating the area we need to find the volume. Volume is area into average height. Now we'll do the first triangle serially. So area of triangle 1, area of triangle is equal to half x1 y2 minus y3 plus x2 y3 minus y1 plus x3 y1 minus y2. Now triangle 1, 20, 0, 12, 18, 12, 15, 15, 3, 15. So that will be half into 20, 12 minus 3 plus 18, 3 minus 0 plus 15, 0 minus 12. Now this by calculating it will be 27. Now volume is equal to area into average height. Now average height is average of z coordinates. Now in case of triangle 1, the z coordinates are 12, 5 and 5. 12, 15 and 15. This will be 12 plus 15 plus 15 by 3 is equal to 14. Now volume of triangle 1 is equal to area, which we just got, 27, into average height is 1414. This will be 378. Similarly, for triangle 2, which had the vertices 18, 12, 15, 15, 3, 15 and 8, 10, 12. Triangle area is half, 18 into, I'll just do it, 18 into 7 plus 8 into minus 9 plus 15 into 2. This is with respect to this formula, half into x1 y2 minus y3. So here x1 y2 minus y3. Okay. Now this will become 28. The average height will be z coordinates, which will be 15, 15 and 12. Okay, I'm sorry, this is average height is 15, 15 and 12. So it is 14. Now volume of the triangle is equal to area into average height is 42 into 14 is equal to 588. Now similarly for the triangle 3, we have the coordinates 15, 3, 15, 8, 10, 12, 10, 0, 10. Now area is half x1, again this formula x1 y2 minus y3. So this will be x1 area of triangle 1 will be 15 minus 10 plus 10 into 7 plus 8 into 3. This will be 28. Now average height will be z coordinates average 15 plus 12 plus 10 by 3 is equal to 37 by 3 is equal to 11. Now volume is equal to, volume of the third triangle will be A3 into H3. This will be 28 into 11 is equal to 308. Now total volume is equal to V1 plus V2 plus V3. Now when we are solving this, is 378 plus 588 plus 308. This will be 1274, which we, according to the options given, 1311 is the closest. So the correct option will be 1311, but when solving we are getting 1274. 1311 is exactly, we are not getting that value. So according to the question, this is the correct answer. So now the next question. Now here we have been shown an object in which we have to find out the containment method of support generation from contours. Now that means that uh, we have to find the support plus object first. Then from that we can find out the supports. Now first is, if we consider this area total, now when we consider this area, consider this as a cube. Okay. Now this object consists of 4 truncated cones. This total, if we consider this one, is 150. This is 60, as it is given here 60, and the width depth will also be 60. Okay. Now when we consider this entire thing, this will be as your support plus object. Now this is saying that we need to consider the containment method of support generation from contours. That means what is the total support for the entire thing. Now why we are not considering this area? This is because there is a rule that if facet normal is upward, we do not need support. If facet normal is upward, we do not need support. So in this case we are not taking the support. Now first we will calculate the volume of the truncated cones. Now for that area, for this region, we are considering it as a cube. This will have the dimensions of 60, 60 and 150. Now the volume is 150 into 60 into 60. This is 540,000. Now this is entire support plus object. Now we need to find out only the volume of the object. After that we will get this volume of support of material by subtracting. Next is volume of truncated cone. Now this is the truncated cone. Okay. volume of truncated cone is equal to half 1 by 3 into pi into h r square plus small r square plus r into r. Now this will be, since we have three, we are considering three cones, that is why we will take it 3 into this total. Now this will be 3 into 1 by 3 into 3.14 into, now height is, the entire height is, each cone has a height of 50. So we will write 50. Now bigger radius is 60, that will be 30. Diameter is 60, so radius will be 30, and smaller diameter is 20, radius will be 10. Into 50, 30 square plus 10 square plus 30 into 10. Now this will be 204100. This is the volume of object. Now volume of support material will be, continuing this itself, volume of support material is equal to minus, earlier we got here 54 54000 54000 minus 204100. This will be approximately 335900. Now in your options it is approximate to option 2. Three three five 900. Answer. Okay, so these were the questions. Any doubts so far? These were the portions to be discussed today. Yeah, yes.
Last week and this week
Okay, yeah. This will I'll be uploading by tomorrow. There were some, actually there were some disturbances, so I could not upload. So actually the entire notes you can access from Drive for the last week, and today's also I'll upload. Yeah. Yes. Yeah. It will be there. It will be there. Yes. It will be there. Everything will be there. Yeah. Okay. Anything else? Any other questions or doubts? No, that NPTEL doesn't provide previous year question paper. Mostly the questions which you will be getting in final exam will be similar to your assignment questions. No, that depends. Some portions are objective, some are subjective. Yeah. So this numericals will be there. That will be subjective itself. Yes, calculator is allowed. Any other questions or doubts or any other clarifications? Okay, so if there are no further doubts, we'll end the session. Let's meet next week again. Okay, thank you all for attending the session. Oh, Okay, okay. Holiday. Okay, okay, good, good. Today what happened, Amma? Today? Rain, now. Today rain. Okay, okay, tomorrow 12. Today not coming, na? Okay, okay. Okay. अच्छा, okay. Okay. Hmm. Confirm. No late, okay, 12:30. Hmm. Home,